In this video, we're going to discuss calculations with entropy. Often this is going to involve the change in entropy, either in the universe, in the system, or in the surroundings. First, let's set up a few relations for how these work together. Remember that the delta S of the universe must equal the delta S of your system, often the reaction, plus the delta S of the surroundings. So how do we find each of these parts? Well, for the universe, we need to know the system and the surroundings. So really we got to find, how do we find the delta S for the systems and the surroundings? For the change in entropy of the surroundings, there are many explanations for calculating out the change in entropy of the surroundings of your system. But the major theory for how we explain this is to look at an expansion of a gas. If you've got a cylinder, it's got a piston in it, and there's some gas. And all around it is the entirety of the universe. Well, there's lots of other material there. There's lots of other molecules to transfer heat and to absorb heat. The universe is so large that even if it loses some heat, if you were to try to then figure out how much is left, it's going to look effectively the same. If you have a large enough surroundings, you can put energy into or take energy out of the surrounding, and it's going to effectively look the same temperature. You're not going to have altered the temperature of the outside by any recognizable amount. This means we can treat it as a heat sink. We can dump extra heat into it or take extra heat out of it as our system requires. But we can maintain a temp, because these calculations are often done at standard temperature of 298 Kelvin. This is the temperature for our standard state calculations. Well, if our piston is to move up, our inside gas can expand. It spreads out. It has more volume to expand into. This increases the number of possible positions and therefore increases the entropy inside our system. However, as the gas expands, it's going to cool, and we need it to stay at 298. So energy has to flow into this to warm it back up, to maintain the temperature. Now, in a real-world situation, due to some random friction and motion, this is not perfectly reversible. Some work had to be done to move the piston, and if you want to push it back down, you'd have to apply some force to push it back down, which is why a car engine requires fuel and burning. It has to perform reactions to cause a piston to cycle. But if you could do this incrementally, infinitely small steps of expansion, and an infinitely small amount of energy being applied, you could avoid any of those losses of energy other than just the exact amount needed to deal with the increased microstates inside the system. Well, in reality, there's no way to perfectly expand this in incremental infinite number of steps, and therefore avoid any energy loss. We can do it mathematically and figure out what it would be. The net effect for this is to make that happen, the delta S of the surroundings ends up being equal to the negative delta H of whatever reaction we're performing over the temperature. This will be true not just for gases expanding, but for chemical reactions and the like. Whatever the heat energy change necessary is, divided by the temperature, that's going to be the change in the entropy of our surroundings. If our reaction was to give away a great deal of energy and be exothermic, you'd have a negative on top, it'd be positive. Your surroundings would increase in entropy, which if you do a reaction that gives off heat, that energy would go into the surroundings and be absorbed, increasing the entropy of the surroundings. If, on the other hand, your reaction is endothermic and requires heat energy, much like this expansion of our cylinder, well, you'll have a positive delta H as it requires energy. So negative of a positive delta H divided by temperature will give you a negative entropy of your surroundings, which in our example here, our surroundings gave away energy to the cylinder. So our surroundings lost energy and lost some of the energy available to put into its microstates. This relation is what we really need to solve for our delta S of surrounding, however. As long as we know the delta H of the reaction and the temp at which we are performing it, we can solve our entropy of it. Delta S of your system, however, which usually is the delta S of your reaction, this we can solve the same way we could solve for the delta H of formations for the delta H of reaction. The delta S for your system at its standard state is going to equal the sum of the S values of its products minus the sum of the S values of its reactants. If you know the entropy of your products and your reactants, when the reaction occurs to go between them, there's a difference in the amount of entropy. As you perform a reaction, molecules you started with had so many freedoms of motion. After you've created products, your products will have more or less based on how many particles you have, how many are gas, how many rotations and vibrations you can have. But since each of those can be known independently, remember that your S can equal the K ln of your microstates. It's a Boltzmann constant natural log of the number of microstates. It is possible to know the actual entropy. These standard state values, the S naughts, are located in the back of the book in Appendix B. And so we can actually use those values to calculate out the change in entropy that our system or our reaction is going to go through. How many more or how many less microstates and how distributed will that energy be among them after our reaction is completed? This means that the delta S of the universe is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants plus the negative enthalpy of the reaction over the temp. If we know these values, we can solve for the entropy of the universe. Is a reaction that we want to occur going to occur or not?